Okay, hello everyone. Today we will learn chapter 12, considerations in designing experiments. So in this chapter we will learn some kind of designing stuffs. So from the problem, if we have some controllable stuffs, then how we can design the experiment. Something like to minimize the variance or something, so something like that. Okay, let's move on. Chapter 12.1 is the element affecting the information in a sample. Recall that a 95% large sample confidence interval for a population mean is this one. And what we can see here, there's two parameters, sigma and square root of n. Sigma and n. So width of the interval depend on population variance sigma square and sample size n. So if we have some controllable stuffs in the experiment, then the one good way to design things is make that experimental setting to minimize this interval. So if we can reduce the variance, or of course, if we increase the sample size, we can uh, decrease the interval. So something like that, that kind of experimental design settings. That's what we will learn. There is two example questions to answer, so you maybe understand what we will dealing with in this chapter. If we wish to compare two populations based on a total of n observations, how many observations should be taken from each population? So we have population A and population B, and we want to compare mean, mu A and mu B. And each of sample we can take NA number of sample from A and B number of sample from B. And if we have restriction that we have a total n number of population that's fixed, then how many we can take from population A and how many we can take from population B? How can we minimize the variance or something? Yes, that's the question that we want to answer. And let's take a next example. If we have decided to fit a simple linear regression model and wish to maximize the information in the resulting data, how should we choose the values of the independent variables? So there's independent variable x and dependent variable y, and if we assumed that the situation would be fit with linear regression, and we want to confirm this result, but if we can control the x variable, if we can control the independent variable, then how we choose the point? How we choose the point of x so that we can maximize the information from this simple linear regression? That's this kind of questions are we will learn about this kind of questions in this chapter. Okay, let's move on to chapter 12.2, designing experiments to increase accuracy. For the same total number of observations, some methods of data collection provide more information concerning specific population parameters than others. Let's consider this example. The difference between a pair of population mean mu1 minus mu2. Let's say there's a first population, population A, and population B. And let's say population A have mean mu1 and variance sigma 1 square. And for the population B, we have hidden parameter that the mean is mu2 and variance is sigma 2 square. And if we want to test about population mean difference, mu1 minus mu2. What design would be better? The option 1 is the first sample we take 5 and second sample we take 5. And in option 2, we take 4 number of samples in population 1 and we take 6 from the population 2. What design would be better? That's the question. And on estimate for mu1 minus mu2 is y1 bar minus y2 bar, and the distribution of y1 bar and y2 bar is as sample size n goes large. This one follows normal distribution with mean mu1 minus mu2, and variance is sigma 1 square over n1 plus sigma 2 square over n2. As when the sample size is large, this would follow this distribution. Then the question would be probably minimizing the variance would be our objective. So when can we minimize this variance term? And actually, we cannot directly solve this one for option 1 and option 2. From here, when sigma 1 square and sigma 2 square, if they are unknown, we cannot directly answer the question. However, if we assume the equivariance, so if sigma 1 square is equal to sigma 2 square, then the problem becomes minimizing n1 plus n2. If sigma 1 square is equal to sigma 2 square, then we can pull out this sigma square sigma term outside, and the problem becomes minimizing this part. And this part is minimized when n1 is equal to n2. So so if we assume the equivariance, we probably go with option 1. Let's move on to example 12.1, which is the generalized question, generalized problem from the previous example. If n observations are to be used to estimate mu1 minus mu2 based on independent random samples from the two populations of interest, find n1 and n2 so that variance of y1 bar minus y2 bar is minimized. So there is population A and population B, and we are taking n1 number of samples from population A. So y11 to y1 n1, and from population B we were taking y21 to y2 n2, and to estimate the population mean, we would use y1 bar, which is mean of these samples, and also we will use y2 bar, which is mean of these samples. And when we are doing the inference about population difference, the statistic that we use is y1 bar minus y2 bar. And to test, we would like to minimize the variance of this statistic. So we would like to look at variance of y1 bar minus y2 bar. And so this is, since these are all independent samples, the variance of this thing becomes variance of y1 bar plus variance of y2 bar, and variance of y1 bar is n over sigma square over sigma 1 square over n1, and variance of y2 bar is sigma 2 square over n2. And so the question becomes minimizing this thing, and we have restriction that n1 plus n2 equals n. So we can change this n2 as n minus n1, n minus n1. And so in here, we want to minimize this thing, and this thing is function of n1, so f n1. So this quantity is function of n1, and we want to minimize with respect to n1, so we will differentiate with respect to n1. And this becomes minus n1 square sigma 1 square, and this part n minus n1 square minus sigma 2 square, but we will multiply minus 1 again, and so this one becomes plus, and we will let it 0, and we will solve it. Okay, so sigma 1 square n minus n1 square, move this to this side, and is equal to sigma 2 square and 1 square, and okay, and this becomes sigma 1 square minus sigma 2 square and 1 square minus 2 sigma 1 square and 1 and plus sigma 1 square n square, sigma 1 square n square equals 0. And from here, this part sigma 1 plus sigma 2, sigma 1 minus sigma 2, and for this part we will separate sigma 1 n, sigma 1 n, and to make it minus of this thing, we do minus here, then we will get for this side minus sigma 1 square n minus plus sigma 2 sigma 1. I don't have enough space, but if you I will write it here, so I will write it here. So minus sigma 1 square n minus sigma 1 sigma 2 n, and for this part sigma 1 minus sigma 1 square n minus sigma 1 square n plus sigma 1 sigma 2 n. If you plus these two, this one cancelled, and sum of these two becomes this thing. So we can write it as sigma 1 minus sigma 2 n 1 minus sigma 1 n times sigma 1 minus plus sigma 2 n 1 minus sigma 1 n equals 0. And so solution for n1 becomes sigma 1 minus sigma 2 over sigma 1 n, or n1 is equal to sigma 1 plus sigma 2 sigma 1 here, sigma 1 n. And actually we have restriction that n1 is greater than 0 and less than n. So we have this restriction, and so if you check this restriction, this cannot be the solution, and so our solution is this thing. And actually you also need to check that the second derivation of f1, so second derivation of f of this thing evaluated that at n1 equals this one, sigma 1 plus sigma 2 over sigma 1n. This is greater than 0. This is greater than 0. And then that's how you show that the function of this function is minimized at n1 here. And okay, so actually, I will leave it to you to check this condition. It's not very difficult, and anyway, n1 is this thing, and n2, n1 is this thing, and n2 is I will write it here. N2 is n minus n1, so it is sigma 1 plus sigma 2. Here sigma 2n. So this is our n2. Okay. Let's consider another example. We are interested in testing beta 1. In our model, y equals beta 0 plus beta 1 x plus epsilon, we are interested in testing the slope parameter beta 1. And if we have the option of selecting n values of x, if we have option to select of x, of which y will be observed, which values of x will maximize the quantity of information on beta 1. Okay, so to answer this question, we would need to check about beta 1, actually beta 1 hat. Consider the standard deviation. Consider the standard deviation of beta 1 hat. Then that's this thing. So from the previous slide, from the previous knowledge from linear model, we learned that the standard deviation of beta 1 hat is this thing. So to do the inference, we should minimize this. We should minimize this variation. And so what it means that we should maximize this quantity. So how can we maximize this quantity? We can put xi's have larger distance from x bar. So x bar is here, x bar is here, and we want to put a larger distance, something like here or here. And also, since we need to fit the linear model, we have small number of points in the middle, but we would like to put larger number of points in the edges, so that maximize this part. So one of a good design for fitting a straight line, if we only have n equals 10 observations, then one option for designing would be something like this. Okay. Let's move on to exercise question 12.1. Suppose that you wish to compare the means for two populations, and that sigma 1 square is 9 and sigma 2 square is 25, and you have n is 90. What allocation of n equals 90 to the two samples will result in the maximum amount of information about mu1 minus mu2? And here, actually, we solved the generalized problem from exercise problem. So, and the answer was n1 is sigma 1 over sigma 1 plus sigma 2 n. And this is, if you put sigma 1 is 3 and sigma 2 is 5. So 3 plus 5, n is 90, and so this is about 33.75, and so the answer is 34. Okay. And what about n2? n2 is n minus n1, and so you get 90 minus 34 is equal to 56. So the answer is for n1 you have a 34, and for n2 56. And let's move on to 12.3. Suppose, as in exercise 12.1, that two populations has respective variance of the same variance. Find the smallest sample size and the corresponding sample allocation that will yield a 95% confidence interval for mu1 minus mu2, that is 2 units in length. So for the 25% confidence interval, that's y1 bar minus y2 bar plus minus, for 95 confidence interval alpha over 2, the equation is something like this: sigma 1 square over n1 plus sigma 2 square over n2, and the confidence interval is so 2 times of this, 2 times and z alpha over 2 for 95% confidence interval is 1.96, and square root of 9 over n1 plus 25 over n2 equals 2. So we need to solve this equation, and here what we know that what we know is n1 is 3 over 8 n, and n2 is 5 over 8 n. So we put this to this inequality and solve this thing with respect to n, then you can calculate n is equal to 245.9, and so and then probably you can take n as 246, and then if you put this one to n1, you can calculate 92.25, and for n2 this is 153.75, and so you need larger than this integer, so your n1 is 93, n1 is 93, and n2 is 154. So you need these number of samples to get 95% confidence interval for mu1 minus mu2, that is 2 units in length. Okay. Let's move on to exercise problem 12.8. The standard error of the estimator beta 1 hat in a simple linear regression model gets smaller as Sx increases. This is because variance of beta hat is equal to sigma square over Sxx. So as Sxx increases, as this one increases, the variance gets smaller. As the x value becomes more spread out, that is, as the x value become more spread out, what it means is that Sxx is sum of xi minus x bar squared. And so in the linear regression setting, if we have, so let's say this is x bar, then if we have more spread values, so all the points here and all the points here, then we would decrease the variance of beta hat. But why don't we always spread the x values out as much as possible? So if this is true, one experiment is if we have n equals 10, then probably we will put 5 here and 5 here. So we have 5 points here and 5 points here. Then probably we would minimize the variance of beta 1 hat. However, we don't do that. We previously in the example we put 2 here and maybe 4 here and 4 here. Why we do that? Why we need point here? That's the question of this problem. And actually the answer is if we don't have point in the middle, we don't know whether the whether it fits linear or the other. Like if we only have data here and data there, then we cannot sure whether the shape of the truth is this one or this one. There are many other possibilities. So to make sure that the equation to make sure that this is linear, then we probably need some point in the middle to make sure that this is they have linear relationship between x and y variable. So the answer is to check for a true linearity or something like that. We need the point in the middle as well. Okay. Here is homework for chapter 12.2. Okay, this is the end of the class today. We will move on to the next chapter, chapter 12.3 in next week. Thank you.